All right, let's jump right in. Think about this for a second. Our entire digital world, from your bank account to your private messages, it all hinges on one tiny hidden thing: random numbers. But here's the kicker. How do you get a computer, a machine that's all about perfect logic and order, to do something truly random? I mean, genuinely chaotic and unpredictable. It's a huge deal for our security, and honestly, it's one of the coolest puzzles in tech.
I mean, really let that sink in. Everything that keeps your data safe, it's like a giant digital fortress, right? And the foundation of that whole fortress is just randomness. So what happens if that foundation is shaky? What if it has cracks? If those random numbers aren't really random, the entire thing could come crashing down. And this isn't some sci-fi scenario, no. It's a real nagging problem that engineers have been dealing with for years.
So, here's the dirty little secret. Most of the random numbers your computer makes, well, they aren't. They're what we call pseudo-random. It's basically a fancy illusion of chaos. It's all generated by a predictable formula. And the weak spot, the Achilles heel, is something called a seed. Think of it as a secret starting key. If someone, say a hacker, gets their hands on that one little key, they can figure out the entire sequence of numbers that comes after it. Game over. The whole thing's predictable. So you gotta wonder, how did we get here? To really get why this new solution is so brilliant, we first have to look at the old way of doing things. The traditional workhorse tool that, well, has some pretty big flaws. And here it is. Meet the LFSR. That's short for Linear Feedback Shift Register. And in a way, this thing is a masterpiece of engineering. It's super fast, it's easy to build, and it spits out these huge, long strings of numbers that absolutely look random to the naked eye. But that's the catch, isn't it? They just look random. Its biggest advantage, how simple it is also its fatal flaw. Okay, the music box analogy on this slide is perfect. Imagine you have a digital music box. You give it a secret key. That's our seed. You wind it up, and wow, it starts playing this super long, complex melody. It sounds totally random, right? But, and this is the big but, if you use that exact same key the next day, it plays the exact same song, note for note, every single time. It's not creating music, it's just playing a recording. And, the researchers who figured this out said it best. Their words are right here. The outputs are typically a deterministic function of the seed. That's the technical way of saying exactly what we just described. If you know the starting key, you know the whole song. It's predictable. Right, so this gets us to the heart of the matter. If the music box is always going to play the same song for the same key, then the only way to make it truly unpredictable is to give it a brand new, totally random key every single time. But where do you get that from? In a computer where everything is built on ones and zeros and perfect logic, where do you find a source of genuine, messy, real-world chaos? And this is where the story takes a brilliant turn. For years, people were trying to solve this by building more complicated algorithms or, bolting on extra hardware. But the researchers we're talking about, they found the answer somewhere else entirely, somewhere no one was really looking. That's it. The solution wasn't in the code. It was already there, hiding right inside the hardware. They realized they didn't need to invent randomness. They just needed to listen for it. They found it not in perfect digital logic, but in the messy, chaotic, physical reality of the chip itself. So let's just make this crystal clear. On one hand, you have the TRNG, the pseudo-random generator. That's our music box, right? Predictable. On the other hand, you have the TRNG, a true random number generator, and that's the goal. It doesn't rely on a pre-written song. Instead, it taps into a real physical source of chaos. It's the difference between playing a CD over and over and tuning an old radio to the random static between stations. We want that static. And what was the source of that perfect random static? It's just the chip being a chip. As any computer chip runs, it heats up, its power supply jitters a tiny bit. These little, unpredictable fluctuations are happening constantly. Now, for decades, engineers saw this physical noise as a problem, something to be smoothed out and eliminated. But these researchers had a total aha moment. They realized this noise wasn't a bug, it was a feature. It was pure, beautiful, physical randomness just waiting to be used. Okay, so the idea is
absolutely genius. Use the chip's own chaos. But how? How do you actually listen to that noise and turn it into usable random numbers? Let's break down how they pulled it off. Well, they used a tool that was already there, built right into the chip, an FPGA in this case. It's called the system monitor, and you can basically think of it as the chip's personal thermometer and voltmeter all rolled into one. Its job is to keep an eye on the chip's own temperature and voltage. It's normally used for, making sure everything's running okay. But in this case, it became the perfect microphone to listen in on all that beautiful chaos. And this is how they put all the pieces together. It's a really elegant process. Step 1, the system monitor is constantly reading those chaotic temperature and voltage fluctuations. Step 2, that messy, unpredictable data is grabbed and used to create a brand new, genuinely random seed. Step 3, and this is the key move, that new random seed gets fed into our old friend the LFSR, but not just once. It's fed in constantly at random times. So what's the result? That predictable little music box is now getting a new random key all the time. It simply can't play its old predictable song anymore. It's forced to improvise forever. Now, that sounds amazing in theory, right? But in the world of security and cryptography, you can't just go on "it sounds cool." You need hard proof. So the big questions were, does it actually work? Is it really random? And almost as important, is it efficient? So they put it to the test. And I mean, they really put it through its paces. So to get the official stamp of approval, a random number generator has to survive what's basically the Olympics of randomness testing. It's a brutal set of 15 different statistical tests run by NIST, the National Institute of Standards and Technology. Each test is specifically designed to try and find any pattern, any tiny hint that the numbers aren't truly random. Basically, for each of those 15 tests, you get a score. If your score is above a certain line, you pass. And as the researchers state right here, their new design didn't just squeak by on a few tests. It passed all 15 of them. That was the seal of approval. This wasn't just a clever idea anymore. It was a certified, provably true random number generator. But what about efficiency? I mean, is this thing a resource hog? Take a look at this. The chip they used had almost 70,000 little logic blocks available to build things with. And their entire super secure NIST-passing random number generator, it took up just 33 of them. 33! That's practically nothing. It's not just effective, it's absurdly, mind-blowingly efficient. So let's just pull all that together. What did they achieve? You get truly random numbers. It passes all the toughest tests. It's completely self-contained, no extra parts needed, and it barely uses any space or power on the chip. I mean, it is the whole shebang. It ticks every single box. Okay, so what's the big picture here? Why does one clever research paper about random numbers actually matter to you and me? Well, it's because it points the way to a much smarter, much more secure future for the technology we all depend on. At the end of the day, what this is really about is a shift in perspective. For so long, we tried to fight against the messy, physical reality of hardware. This research shows us we should embrace it. By tapping into the chaos that's already there, hiding inside the chip, we can build a stronger, leaner, and just more elegant foundation for all of our digital security. And that really leaves you with a final, fascinating question, doesn't it? They took something everyone saw as a problem, physical noise, and turned it into the solution. It just makes you wonder, what other amazing, elegant answers to really complex problems are out there, hiding in plain sight, right inside the tools we're already using?